Okay, so in today's lecture, we are going to look at some various kind of stuffs about how artificial intelligence is playing its role in the domain of control engineering. So the title for today's lecture is Teaching Controllers to Think: The Rise of AI-Driven Control Engineering. Okay, so these are the contents of our today's session. We're gonna start with looking into the what is control system, what is control engineering. We're gonna look at some of its fundamentals and some of the basic techniques that normally we use in these control engineering concepts and how we normally go from theory to actual technologies, right? And then we're going to see how we incorporate AI-based algorithms into these hardware equipment. And afterwards, we're going to see in which various domains of engineering we have already incorporated these AI-based algorithms. Okay, so yeah. So we are going to start with the basics of how a control system how it work. Okay, so this diagram is a block diagram that represents how the architecture of controlling any kind of equipment that exists in the hardware world works. Okay, so we have something called a plant, a system that we're going to work on, and we have something called a controller that is basically controlling that system. Okay. So the job of the controller is to generate and send signals so that this system does some stuff that we want it to do. Okay. So how does the controller know what signals to send to this system? Okay, so we basically tell the controller, we give it a reference signal, we tell it this is what we want. After we have told the controller this is what we want, it's the job of the controller to ensure that it generates signals in such a manner, signals in such a manner that this plant or the system that we're working on does exactly what we want. So once we get some kind of output from the system, we try to measure it. Okay, using some kind of sensor or anything, we measure the output to compare the signals and see if the system actually did what we want it to do in the first place. Okay, so this is a closed loop system in which we are also measuring the output as well. Okay, so we have our initial reference signal, that is the signal that we tell the controller this is what we want, and then the output signal that is the actual output that we have received. So we compare these two and we see, okay, this is what we wanted, and this is the signal that we are getting as an output. We compare these two and calculate the error. It is the difference between what you wanted in the first place and what you're getting. The difference between these two is called the error of the system. This error is fed back to this controller, and this controller tries to remove this error. So once the error is removed, so you are basically getting your reference signal equal to your output, which states that you are getting exactly what you would want in the first place. Okay. So here in this part, this controller that makes the decisions of all this stuff, what to do and how to do, there's equations, mathematical equations behind these controllers. And those mathematical equations comes from the laws of physics. So every time this controller has to make some kind of decision, it has to solve complex mathematical equations. Okay, so we'll see later on in this lecture that while incorporating AI, what we try to do usually is this. Instead of having to solve complex physics equations at every instant of time, what we normally do is learn from patterns and solve less computationally expensive equations using AI algorithms. So we incorporate AI algorithms in place or in conjunction with these controllers so that our computation is much faster and it is less expensive as well. So if it is less computationally expensive, that means we can get it done. We can get the same good performance using cheaper equipment. Okay? Because sometimes the equations, the physics theories that are behind this controller part, which is the brains of the overall system, whatever you are trying to control. So this brain is so computationally expensive sometimes that it requires really, really expensive equipment to process those equations. Okay, so what we can do is use AI algorithms to learn from those equations and make decisions based on those training, which is less computationally expensive. Okay. So moving on. So we can design, well, there are different kinds of controllers and algorithms in this controller block. We can differentiate these different types in two categories. One is the linear controllers, which is comparatively easy and it's not computationally expensive and it is being used widely throughout the world and it does work pretty well. And then there is something called non-linear control. Okay, so there is a linear control and there is a non-linear control. So the nonlinear control is the computationally expensive but very accurate. It does require a lot of processing. It does require costly equipment, but for every complex system, we have to go for nonlinear control theory, okay? Because linear controllers do work pretty well, but they fail in complex scenarios, okay? So here I have an example that I was flying this drone and applied a linear control system. So I gave it a little jerk and it worked fine, but I gave it a little harder jerk and bam, it crashed. Okay. So initially, if I play the video again, initially you see the drone is working really, really good. Okay. So this is our normal linear control. Once I give it a disturbance, so that disturbance is a complexity. So it wasn't able to handle that complexity. Okay, so that is what happens with link control technology. So it does work really well, but within a limited range of operation. You can't you can't have complex scenarios and use linear control. So if you want to like have an automatic water dripping bottle maker machine type of thing, or a special pick and place kind of robotic arm and simpler stuff, yeah, linear control is always a good choice. But if you want to have complex scenarios like uh, a fighter jet performing vertical flips or back flips, then that's a complex scenario. Then you need nonlinear control theory. But yes, we can always get that nonlinear control theory, but the problem would be that it is quite computationally expensive. So sometimes we do incorporate AI algorithms with those equations of physics. So to overall increase and reduce the computational cost and increase the performance of that system. Okay. So here is an example of a nonlinear algorithm working on a drone. So this person is holding the small drone in his hand, and the drone is initially turned off. Now he throws it in the sky. While it is being thrown, it was flying and it autonomously flies and hits the target. Okay, so we can have a look at it again. So the drone is initially turned off in its hand, and throwing it into the air is a huge disturbance, and a lot of physics is involved to make it fly. So it does not fall to the ground, it flies, it takes a mission, and bang, goes to the target and does its job. So this is what we can expect from a nonlinear control theories, right? So we use nonlinear control whenever there's something complex to tackle, and we can use always linear stuff with a lot of simple tasks, right? Because if the task is complex, the linear control is going to fail. So now that we have established there are two major types in control engineering, which is the linear control and nonlinear control. And now we know that for simpler tasks, linear control is good. For complex tasks, linear control fails, so we have to go for nonlinear control. Now that we understand where which control type applies, uh, we understand in most of the world, our actual systems do fall under the category of nonlinear control. So we do have nonlinear, very well nonlinear control established, but the thing is that it is quite computationally expensive, and sometimes we just have to go make approximations. So to make approximations, we have to do that because we do not have good equipment, or we would have to increase the cost of the system. So to reduce the cost, increase the efficiency, improve the algorithms, what we do is we incorporate AI with these nonlinear control theories. So we'll see how we can do that. Okay. So once we design all of these algorithms in the computer, what we normally do is, we plot its results. Okay. So we apply different kinds of algorithms. All of these are the names of some of the algorithms, the non-new control algorithms that give different performances. So we wanted a perfect helical trajectory. But the color indicates the legend. From the legends, you see that different kinds of algorithms did perform very well, but initially they were very far away from that starting point, except for this cab-dist SMC, right? So this cab-dist SMC performed really, really well. It initially started to track and went all the way throughout this helical trajectory and tracked throughout. So different algorithms performed differently, and of course, in nonlinear control as well, we can't always expect all of them to well behave perfectly, right? So different algorithms would have different kinds of performances. So this algorithm starts to move from here and goes all the way over to throughout the journey. It does a very good job in comparison to the all of those rest of the algorithms. So we plot what behavior we can expect from the system using different kind of algorithms, and we establish which algorithm is good enough and for which should we go with in the first place. And then once we have established it, we have designed the algorithm in the computer. So what we do is we use the computer along with the hardware. So we send the programming signal to the actual hardware, and we get the feedback back to the computer. Okay, so we make a connection of our computer with the hardware, and we then test it. Our algorithm was performing really good in a simulation. So how is it going to perform in a hardware situation? So we use this controller in loop experiment in which our computer is physically connected somehow connected to that actual hardware equipment. We incorporate our algorithms onto that actual hardware and we see how it works. So from designing the algorithm in the computer and simulating it, seeing how it works, to moving to actual hardware. Okay, so we use the same code that gave us really, really good performance in the simulation to this hardware domain. So this is an example of a drone being connected to that simulated environment via this data cable. Okay, so we normally use data cable to charge our phones as well, and if we sometimes want to transfer data from our laptop to the mobile phone or to the mobile phone to our PC or laptop, we use this data cable, right? So the same kind of data cable is being used to transfer the programming algorithm that we designed in the computer using laws of physics and nonlinear control engineering theory concepts. We transfer this to this hardware equipment, and then we see how it works, how this drone works in the first place. Okay, so this is an image of the setup. So once that is done, Once that is done, what we sometimes do is this, that uh, we can incorporate something called a reinforcement learning. Okay, so that is very near to how we can use AI and intelligent algorithms to, well, increase the performance and increase the performance of the non-linear control algorithms that we already designed. So the way it works is that uh, we design a policy, okay, so that we want to do this, we want to get that thing done, and in accordance to that policy, an action is done, which is how a signal is being sent to the actual system. So once the actual system receives the signal, it gives an output, and that output is observed and measured. So based on that output, there is something called a learning algorithm that always tries to update the policy that we initially set up. So initially we say, okay, so this is our policy. If this happens, we have to do this, this, this. So once we implement our policy, we see what happened with this implementation, and we see, okay, we got this kind of output. Now we need to update our policy. So at every try, it keeps on self-improving based on the learning algorithm. And every time we give it a reward as well. So if the output is good, we give it a reward, so it goes into that direction. If the output is bad, we give it a little less reward, so it avoids doing that thing again. Okay, so this is the basic concept of reinforcement learning. So in a nutshell, what reinforcement learning does with our controllers is that every time the controller makes a decision, our reinforcement learning algorithm ensures that it learns from its past and keeps on updating itself so that it makes better decision in the future. Okay, so this is one of the examples of how this reinforcement learning AI-based algorithms can be used uh, along with or sometimes instead of those complex physics equations. Okay, so moving on. So this is an article in which deep and reinforcement learning based non-linear control algorithms were used for a UAV system, unmanned aerial vehicle system, and a lot of detail is given here. But I'll go ahead and show you what happens here. Okay, so a neural network, which is some domain of artificial intelligence as well, AI-based algorithm was used in a hybrid mechanism with that controller. Okay, and we got almost the same good results, but the major difference was using that nonlinear control theory, the simulation time was taking 2.3 seconds every time it had to make a decision. Using the physics laws and having to solve all those complex mathematical equations, every time it had to take this 2.3125 seconds for every decision. So when we use the AI-based algorithm, it reduced by many times. So every time it had to take the action and get the same kind of result took only 0.03 seconds. Okay, so that is about 75% times more faster. Okay, so by choosing just the AI-based algorithm, with those physics laws, we increased the computation time, or would decrease the computation time, increase the computational efficiency by 75%, more than 75%. So that's a huge number. We're getting same performance, but every instant of time, we are taking 75% less time to execute every decision that we have to make. Okay, so in that is a very, very well, very impactful direction. Okay, so that moving on. So once all of that is established, then we establish some kind of hardware setups and we see how the algorithm is going to perform. So we have all these equipments and all these things patched together, and we will implement the control algorithms from the computer, and all these sensors and readings, all of them will go to the actual hardware system, and we see how our simulated algorithms are going to work in the actual hardware system. So once it does that, then we are good to go to actually implement the actual system, right? So this is an example of a PID controller that I implemented some time ago. And during the test, okay, sometimes it gives bad performance, sometimes it gives good performance. So like I told you that it always tries to update the policy. So initially you see there's a huge jerk and the performance was not good. Then on the next iteration, it performed better than before. And at every instant of time, it was always better than before, and better than before. So ultimately, this is one we implement, and then the performance is really good. You see now, while hitting it initially, we saw that it took a good flight, but once given a disturbance, it failed. Now with the knowledge control algorithm, so that's a disturbance here, and again a big disturbance, and still it comes back, and it is flying really, really good.
Reminding you, brothers and sisters, you are with Atlantic International University and you are following this class on AI-based aerial systems or drones. I'm not sure whether we have lost our presenter, Abdullah Magiz. We don't seem to be getting any audio nor video feeds from Magiz. Apparently, there is an issue with the network where Abdullah Magiz is making his presentation. That's a very unfortunate event for the first Monday of this year, 2026. Let me look around to see what might have happened. I have lost Abdullah Magiz. He was telling us, brothers and sisters, about the extent that artificial intelligence can be used to make drones perform better. And of course, I do understand we were to deal with a huge amount of technical data, which can be sort of difficult to assimilate, to manage, but let me inform you that you can contact your tutors if you want to get a replica or of this presentation, although it was interrupted. We still don't have contact with Professor Abdullah Magiz, but let me again uh, precise for you, brothers and sisters. We no longer put those entire classes, those full sessions onto your student portals, but you still can review those sessions by contacting your tutors, not your advisors, your tutors, who will do the necessary diligence to make sure that you have access to those presentations. All right, Abdullah Magiz is back. I'm very happy for that. I just admitted him. Let me see if Abdullah Magi has logged back in. This is our wish. I'm keeping my fingers crossed, hoping for the presenter to become available to us so that he can eventually continue the class and also wrap it up as soon as possible. We still have a good 27 minutes to go. I just admitted Professor McGee, but do not see the name in the mosaic screen that I have right in front of me with all the faces and names. Please bear with me, brothers and sisters. I'm doing my very best to ensure that we get Abdullah Maggi back. So he was gone again, probably a situation with his network. I admitted him, but he was kicked off again. But I am pushing to get him back. I just admitted him, and hopefully he'll be able to be with us very, very soon. Not as of yet, as far as I can see. In the meantime, if you have a question of a general nature, all right. I see Professor McGee. Let me turn his microphone on. Thank you very much for your diligence to get back to us, Professor McGee. Let me unmute your microphone.
Hi,
Okay,
sir.
good,
Apologies, my
super.
just
That's okay. We
yeah.
do understand. Things happen. All right. So uh, you are in full power now to resume your presentation, please.
Okay, thank you. Thanks a lot. Okay,
You're
so
welcome.
hi everyone. So I was here telling you about. So once we implement this knowledge control, we can observe that the performance was really good even with huge amounts of jerks. So indeed, these algorithms, see, there's a huge amount of disturbance, and initially the linear control all failed, but these non-linear control algorithms, they do work really, really well because of the incorporation of reinforcement learning based, which is a part of AI as well, we can say. So it does keep on updating itself from the previous mistakes. And as you can see, I'm giving it a good amount of jerk as well. So that's a good amount of disturbance. And initially we saw that it failed now, but now it is crackling. So that's a really, really good performance we can see here. Okay. So now let's talk about little how we actually incorporate those AI algorithms. Okay. So what we do is that we can't replace the equations of physics using some other kind of logic, right? So what we do is we use those equations of physics and we give it thousands of inputs and see how uh, thousands of output that controller is going to give by solving all those complex physics and mathematical equations. So we let a supercomputer run for once all those iterations for thousands and thousands of decisions, and we save the data. So we save the data, and now we have this information. Okay, if I give this input, this controller that is going to solve all that complex equations is going to give me this answer. Now, if I have this input, it's going to give me that answer. If I have this input, it's going to me get that answer, right? So I have thousands and thousands of data of inputs. So if I give it that, it's going to give me this kind of output. So I have this data. So every time I give it some kind of input, I know what kind of output I'm going to get. And of course, at every time while I was saving the data, it had to solve that complex equation. So I did use a supercomputer once, but once I have this data, now I know thousands and thousands of decisions for every different input it is going to make. So once I have all of this data, which is a very unique data, so then I can use some kind of AI algorithms that learns from data. Neural network learns from data. Machine learning algorithms learn from data. So I can use some kind of algorithm to learn from this data, and then I can just skip this controller and all of those complex computations, right? So I know what the decisions it is going to make, and I have an algorithm that understands what kind of decision it was going to make. So it behaves in a similar manner. It behaves in a similar manner without having the need to compute all those complex equations. For example, if the input was given to 10, okay? So if the input was given at 10, then the output was 100. If the input was 100, the output was 10,000, let's say, okay? So if the controller was to perform, it would have to, well, compute complex equations. It would take 2.3 seconds to deduce that. If the input is 10, it is going to solve some equations, which is going to take 2.3 seconds, and it is going to give you, okay, so the output is 100. But the AI algorithm who learns from the behavior of the decisions, it knows that, okay, if the input is 10, fine, the output is 10, the output is 100. It gives you answer in 0.03 seconds, which is exactly the same as the original one, but it is not computing any kind of equations. It is just learning from the behavior of those decisions that have huge amounts of data. So this is how we merge AI algorithms with the control theories. So we'll let it run for once with using some kind of supercomputer, and then we collect the data, and then we use some kind of AI algorithm to learn from that data and then incorporate that, and that is which is very, very less computationally expensive. Okay, so moving on. So now that we have seen that how we can how we actually incorporate AI algorithms with control engineering concepts. Huh? Now let's talk about some real world applications. So this kind of AI-based nonlinear control, artificial intelligence based nonlinear control is being used in various different kind of domains. It is being used in biomedical engineering. For example, it is being used in chemotherapy, in chemotherapy operations as well, in tumor patients, in prosthetics, and in making pacemakers. It's being used in a lot of different kind of stuff. This AI-based volume control. It is being used in renewable energy resources as well. It is being used the the uh, wind turbine systems, solar inverters, the grid stations, and all those electricity generating stuff from these all these equi- uh, all these grid stations that we wanted to work with in the first place, right? Okay, so then uh, it is being used in UAV systems as well. It is being used in drones and systems as well. It is being used in electric vehicles. It is being used in power grids and much more. So here are some of the well, applications of how these AI-based non systems can be used. So here it is being used for trajectory tracking of a quadcopter system. Okay, so trajectory tracking is you give it a navigation system. It's okay, you have to go from here to there to this point to that point, all this and that, moving to that final. point. Okay, and then moving on to the next. So it moves, it is being used in electric vehicles as well. So this nonlinear control theory was being used in hybrid electric vehicles. So how it was being used is that we have some kind of power stations, okay? We could have a wind turbine or a solar inverter or any kind of ultracapacitor system or a hybrid energy storage system as well, or fuel cell or any kind of different kind of multiple hybrid energy producing systems, but they do need to provide a constant amount of energy to these electric vehicles. So, to provide stable and constant amount of energy to these electric vehicles, we do need to stabilize that voltage levels. So, to stabilize those voltage levels, you know, specific decisions have to be made in those electronics. So, this nonlinear control engineering using the AI algorithms, like the way I told you in these EVs, do that as well. Moving on. So here in this research, this control algorithm was being used for treating the patient that had brain tumor using the chemotherapy. And moving on, here another biomedical engineering application is placed in this research work. The authors used these algorithms to cure blood glucose concentration for type 1 diabetes patients. And here's another research. The authors here used these algorithms with all of these renewable sources for again a hybrid kind of electric vehicles. And here is a very different kind of work as well. So the authors use these algorithms here for magnetic levitation system. That is the basic phenomena that is used in bullet trains and the rest of the details. And here another uh, example is that the authors here use these algorithms in a hybrid AC-DC microgrid systems. Okay, so we can have an island here and there, and we need to sometimes to utilize electrical energy on those islands. So there, these microgrids are the solution. So to have stable and sustainable microgrids, we use these kind of algorithms all around. Okay, so these are some of the case studies that we saw that how these AI-based nonlinear algorithms are being used in very different, various kind of industries and how they play a very vital role. So to conclude this presentation, control engineering is evolving from fixed rule design towards intelligent and adaptive systems. We saw that linear controllers perform very well, but in a limited operating region, while the nonlinear controllers ensure stability under complex dynamics. AI techniques, especially the reinforcement learning and the BIOS and the neural networks, they do significantly enhance the controller's adaptability and performance. We saw that using some examples as well. And we can safely say that intelligent control frameworks are already being applied across various different diverse sectors, including drones, UAVs, EVs, electric vehicles, biomedical systems, renewable energy, smart grids, and much more. So, if we talk about the future work and the future directions, what we can say is that we can go ahead and look into the development of hybrid AI nonlinear controllers for extreme and uncertain environments. So, like I was pushing the drone, that was a good uncertain environment, but we can go for extreme conditions as well and see how well it behaves. What are the boundaries of the complexity that it can handle? We can go ahead and see the extension of control strategies to highly complex and nonlinear UAV missions like harsh weather conditions. We can send it through some tsunami or stuff like that. We can go ahead and see the experimental validation of on diverse different unmanned and autonomous platforms. We can always have the exploration of advanced variants of nonlinear control algorithms and explore how they're going to perform well. And once we have good performance using these nonlinear control algorithms, we can use AI robust for improving the robustness and performance and reduce the computational expensive cost. Integration of more data-driven learning techniques for real-time adaptive control. So we can always use the latest data-driven learning algorithms to do the stuff that we learned today, and we can always compare its performance and see which is good and better. So that's pretty much it about today's lecture, and now it's up to the audience. Thank you, Doctor.
Very well done again, as expected, Professor Abdullah Magiz. Despite the brief interruption, your delivery was up to par, so to speak, and the entire family of Atlantic International University is thoroughly happy with your presentation. Thank you very, very much.
Thank you.
We can't wait to have you again for a similar presentation. Ladies and gentlemen,
Thank
it
you.
is your turn now. It is your time. The floor is entirely yours. I am so sorry. So many of our traditional attendees were not present today, probably as a result of the length of their holiday. They have not come out of the holiday as of yet. But for those of you who were with us today, there is no doubt you have enjoyed the session. Of course, what we are dealing with is a huge, humongous amount of difficult technical data when it comes to aerial systems. The terminology is not very, very easy, but Professor Abdullah Magiz, with the case studies, with the examples that he has provided, he has made learning a bit easier and pretty much like I pointed out during the interruption, you can get in touch with your tutors so that you can get the whole presentation at your leisure time so that you can review the data and eventually commit yourself to mastering, to assimilating, and to becoming experts. You also in this field of aerial system, particularly like Professor Maggie indicated, that is the trend of the future. No matter how difficult the terms can be, no matter how hard getting into this area can prove to be, there is no doubt that is the trend of the future. You've got to do whatever it takes to learn to become comfortable with the field. So, at this time, brothers and sisters, remember there is no uh, questions that are kind of nonsense or stupid, like some teachers have said. I remember when I was little, whenever there was something that I did not understand or some other students did not understand, they raised their hands and they asked questions. And of course, people ask questions about things that we do not understand. And some teachers would say, "Hey, get you there, get you here." They were getting mad. And some of them found that our questions were stupid. But there is no such thing, ladies and gentlemen. No matter what it is that you did not quite get, this is your time. Raise the issue and Professor Abdullah Magiz would be certainly very happy to address whatever concern you raise. He will joyfully respond to your questions. The comment we have in the chat box is not actually a question from Emmanuel Owure, but it's a request, Professor McGee, and this is what Emmanuel Owure would like to see happen. Can you share a link where I can do more reading on this topic? This is a question from Emmanuel Owure. Let me repeat it. Can you share a link where I can do more reading on this topic? I don't know if you have an answer for him, Professor McGee's.
Yes, definitely. I'm searching it right now, and I'll share it in the chat box. Meanwhile, we can go to the next question.
All
I'll
right.
share the link right now. Thanks.
Ladies and gentlemen, let me repeat this. It is your time at this moment. Do not hesitate, no matter how little or how apparently simple, whatever it is. If you have something in your mind, something that Professor Abdullah Magiz mentioned, which proved to be unclear to you, please, I'm begging you, do not hesitate, don't be shy about it. Go ahead, either live, make your voice heard, or if you prefer, like Emmanuel, go ahead in the chat box, type in your questions in there, and I'll read it for Professor McGee, and he certainly will answer. As we are waiting for you, let me fabricate a question of my own. And I'm certain that the answer to that question from our presenter will certainly prove useful to everybody. Professor McGee, we are talking about algorithms. This is a concept that is sort of new for many people, and we do understand that those algorithms do allow us to make very, very, very complex things, situations where human mind would be powerless, helpless, but with this advent of artificial intelligence, we can make things happen through those algorithms. Is there any way, Professor McGee, you can explain that concept to our class without mentioning the term algorithms, but trying maybe, this is my question, to make it very, very simple in easy chunks of words that everybody can understand. What are they, Professor McGee, those algorithms?
Okay. Okay. So thank you so much for your words. And okay, so I'll try to explain all these complex algorithms in some simple forms. So whenever we want to make a real life system, we just don't want to make it. We want it to obey us as well. Okay.
Okay,
So
okay.
to ensure that it obeys us, we have to incorporate some kind of artificial brain into that, and we have to ensure that brain obeys us. We don't want to
Okay.
make any kind of system that does not listen to us. Okay.
I
So
got it.
then what we do is we study all that physics phenomena that is applicable to that system that we are going to make, and based on laws of physics we understand, okay, if I want to make this happen, then I have to give this kind of input so that that will happen. So based on the laws of physics and engineering concepts, we are able to make algorithms that once incorporated into the system that we are making, it will ensure that the system behaves according to our wishes.
All right. There is another point
Yeah.
being brought up in the chat box. If I'm not good at math and physics, can I get involved in artificial intelligence? if I'm not good in
Uh,
math and physics?
okay, so a few years ago, I would have said no, but now
Ah,
definitely yes. Because
okay.
if you're not good at something, that is fine. You have your best friend, the AI assisted models, the ChatGPT, the Gemini, and the stuff like that. You can always tell it, I'm not good at this. You tell me what do I do. So it does compute those equations and does all that complex work instead of you. So you can always get into every domain these days.
Very, very clear answer, brothers and sisters. This is what we've been waiting for. It is easy, according to Professor Abdullah Magiz, to get things done, no matter how complex a narrative sounds or looks or whatever endeavor or activity we want to get involved in, you can get it done because those
Yeah.
multiple artificial intelligence platforms out there to assist you. Whatever you have in your mind, whatever is conceptualized in your mind, you can make that become a crude reality going through either one of those artificial intelligence platforms. Thank you very, very much. In the meantime, brothers and sisters, and particularly for Emmanuel, who brought up this issue, and of course for everybody else, Professor Abdullah Magiz has just placed a key document into the chat box for you. So I would right now very highly recommend that you go in there, and all you have to do is either click on that link or highlight it and copy it so that later on, or even now, I would preferably suggest later on you can go to any browser that you use and plug in or paste that website, and this document will be in your hand. So go ahead, please, before we close the session. Go ahead and do it now. The link is currently in the chat box. Please go ahead and do that before we close the session. As I was also saying earlier, there are some faces that we are all familiar with, and for whatever reason unknown to me, and certainly which you do not understand or know either, those familiar faces did not join us today. It's very, very unfortunate. But of course, the document is there. Uh, Let me remind you, brothers and sisters, you may get in touch with your tutors, and they will make sure if you have missed anything, you can then get access back to this presentation. With this last comment, ladies and gentlemen, we have come to the end of this class. Personally, every time I have an opportunity to learn about artificial intelligence, about UAV, unmanned aerial vehicles, this type of modern technology, I feel happy because I keep saying it is the trend of the future. It is what the entire world will be made of, and I highly recommend that you also jump onto the bandwagon of learning about these things. As we are closing this session, we're gonna get back momentarily to our subject matter expert, Professor Abdullah Magiz, for his conclusion. But you can see, looking at the mosaic screen in front of you, brothers and sisters, a brilliant face right now. It is our provost, Dr. Ricardo Gonzalez. Thank you very much for joining us today. I know you are always there, but sometimes I do miss your video feed, which we now have, and I thank you very, very much for sharing that video feed with the entire family of Atlantic International University. Thank you very much, Dr. Ricardo Gonzalez. And at this time, we're going back to our presenter, Professor Abdullah Magiz, for his concluding remark. Please, Prof.
Okay, so thank you so much, Doctor. What I would say is that if you like any of this into this lecture, any kind of domain, I would recommend you that you take an introductory session from YouTube or any kind of course. So once you have the little details of about the fundamentals of that domain, then you can use the AI models that are freely available to everyone to get into the complex details without having the need to know the exact mathematical detailed computations, and you can get done some pretty good stuff. So try to use the AI-based models that we have today to the best of your ability to get some good stuff done that you wouldn't be able to do a decade ago.